So in this video and on this worksheet, we're trying to figure out what is the best way that we can do to maximize an area of a different shape. In fact, we're trying to maximize the area of a rectangle. Okay, so maximizing area of a rectangle, and it says here that we have a fixed perimeter. Okay, so no matter what shape of our rectangle, we have to have a perimeter of 150 meters. Okay, so our units are in meters. Sorry, this is not American this time. This is standard operating procedure. So we have a rectangle. Okay, so we're going to first draw in your rectangle and put down the two formulas that we know for your rectangle. Okay, so if this is the length and this is the width, what is the area formula for a rectangle? Area equals length times width. Okay, it's a product of two dimensions and it has a squared unit. And what is the area, or rather, what is the formula for the perimeter of a rectangle in general? Two lengths plus two widths. When we simplify it down and combine your like terms and make it as easy as possible. Two lengths and two widths. And in this case, in fact, we know that the perimeter is going to be 150. So in all of these problems we do, we always start by first writing down your two equations. We have an area equation and we have a perimeter equation where we know what the perimeter is. Okay, and your second step, because it's very procedural and recipeed, right, repetitious, is to just make a decision. Do you want to keep L in your problem, or do you want to keep W? Because we can only find one variable at a time. Okay, so you have to decide, do I like L better, or do I like W better? And it really doesn't matter which one you do. So I'm going to pick, just for fun, I'm going to replace my L. So I'm going to say, and I put a box around it to remind myself that I am replacing my L in my area equation. Okay, so if I'm going to replace L in my area equation, that means I have to solve for L in your perimeter equation. Because what I'm going to look to do is substitute one variable for another one. And I can't substitute unless I have equal. So I'm going to do all the math I need to do in order to solve this equation for L. So the length is going to be 75 minus the width. So now that I have that, I'm going to replace. I'm going to take my 75 minus W and I'm going to put it over here in my area equation. Since I want to maximize area, this is the equation that I need to work with. So that's what my equation looks like now. The area is 75 minus W, right? Because that's how you calculate your length, times W. My two dimensions are multiplied together. So with a little bit of distributing here, I can simplify my area equation to 75W minus W squared. And this is, of course, your quadratic. So if we want to be optimizing a quadratic, this is the quadratic that we want to optimize. Okay, so what does an optimized quadratic look like? Well, remember, we're trying to find the area. So let's come over here and look at a graph real quick. I'll just make a graph. Okay, so there's my y-axis and here's my x-axis. Well, actually, area, right? Area is your dependent variable. So area is your vertical axis. And our independent variable is W. So the width is along your independent axis. So my graph, my quadratic graph, my parabola, is going to be a width comma area. So as the area, and notice it's a negative W squared. So this parabola is going to be opening down. So my parabola is going to look like this. As the width increases, the area is going to increase up to a certain point, right? And then the area is going to start getting smaller as the width gets larger. Because, of course, as the width gets larger, the length changes, right? So eventually we're going to have a really really skinny little triangle or rectangle. Okay, so this point right here is the maximum value. Okay, so this is a certain width that goes along with the maximum area. So the independent variable, or W in this case, is the x-coordinate of your vertex. Right? This is the x-coordinate of the vertex. And then the y-coordinate corresponds to the actual area of that rectangle. Okay, so there's one formula that we use anytime we're asked to find the vertex, and that is x equals negative b over 2a. So make sure you have this written down somewhere. You use this every single time. Okay, and that's talking about the x-coordinate of your vertex. So for us, in this problem, we're actually going to be solving for w. Right, so w equals negative b over 2a. Now, where do these letters b and a come from? Because all I see are w's in a uppercase a. Well, they come from the fact that your standard quadratic is ax squared plus bx plus c. Okay, so this is the standard form of your quadratic, where a is the coefficient of your squared term, b is the coefficient of your single power variable term, and c is your constant without a variable at all. Okay? So a comes from your squared term, and b comes from your variable or your x term. So let's see if we can identify those over here in our 75w minus w squared. So which of these two terms is a and which one is b? A is the thing in front of w squared. So what is the thing in front of w squared? Negative 1. Right? You don't see a number, but you do see a minus, so we can assume there's a negative 1. And our b term is going to be 75, right? Because that's the number in front of your normal variable. Right, so it's not in standard form. Standard form would be negative w squared plus 75w, right? Because it goes from highest power to lowest power from left to right. So maybe if you want to rewrite it in standard form, you might be able to quote unquote see your numbers better. But the a is always in front of your squared term, and the b is in front of your single variable. So now that we know that, we can figure out what the width is. What is the width, the x-coordinate of your vertex? Is the negative of 75, because it's negative b, divided by 2 times negative 1, negative b over 2a. Okay, and what we're going to find is the w, or the x-coordinate of your vertex, the width that goes along with the maximum area. So when I do this, negative 75 divided by negative 2, that's not a 75, that's a 72. Negative 75 divided by negative 2 is positive 37.5. Okay, we should never be getting a negative anytime we're doing a dimension, because dimensions are always positive. Whether you're going up or down, dimension is positive. Forward or backwards, dimension is positive. So we have a width of 37.5 meters. Now to find the length, we simply plug it into that equation, right? We know the length is 75 minus whatever the width is. So what is 75 minus 37.5? Well, it turns out that is 37.5. So I've calculated my width of 37.5, and I've calculated my length also of 37.5. So what are the dimensions? Well, they're 37.5 by 37.5. So now if I multiply these things together, I can actually figure out what the greatest area is. 37.5 times 37.5 is 1406.25 square meters. Okay, so this would be, in fact, the maximum area of your rectangle, with a perimeter of 150. Okay, those are the dimensions that will maximize the area. Okay, so your steps are done the same way every single time. Okay, you write down your perimeter, you write down your area, you decide what letter do I want to keep. And it doesn't really matter which one you do. Okay, but you replace that one by solving for it on the other side to make a quadratic that you're going to then find the vertex of. So try that on number 1. We'll come back with all the work here in a minute. So pause the video, right? Do the work, and we'll be right back. So our farmer should have a 2.5 by 2.5 kilometer rectangle. In other words, a square with an area of 6.25 square kilometers. Okay? So you have your area equation and your perimeter equation with a perimeter of 10. So the length is 5 minus the width. Right? We plug it into our area formula so we get a quadratic. From your quadratic, we find the vertex. Right? So we use negative b over 2a, and we get a coordinate of 2.5. You plug that back into your formula to get the other dimension so that you have both of your dimensions that you can multiply together to give you the area. Excellent job. Okay, on to example 2. Mr. Jones wants to enclose his backyard so his new puppy, Sebastian, doesn't run away because he doesn't believe in shock collars or invisible fences. So he has 400 feet of fencing material, so that's going to be his perimeter, right? The perimeter is the amount of stuff that goes around the outside. One side of the enclosure will be along the house. So what are the dimensions of a rectangular enclosure that will maximize the area, right? That is our goal, is to make the biggest area possible for little Sebastian with the amount of stuff that we have. So let's look at our rectangle. So part of our rectangle is formed by the house, right? So all this is house. We don't have to put a fence along the house. So that means we only have to enclose 3 sides of your rectangle. We have one length, one width, and another length. Okay, so if we don't have a random rectangle sitting out in the middle of a field, right, this time we have our rectangle against the house, you don't have to put a fence along the house because there's already a barrier there. The dog can't run away through the house. So our perimeter is going to look a little bit different, right? Our perimeter is 2 lengths plus only 1 width because we are only enclosing 3 sides of our rectangle. Your area formula is still the same. Area is length times width. So now, looking at your problem, I have 2 L's plus 1 W. So it might behoove us if we were to solve for W. So let's just replace W here because W is really easy to solve. I don't know so about really easy, but W is mathematically easier to solve for than is L. So by simply subtracting my 2L from both sides, now I have solved for W, right? There's no division whatsoever. Okay? So it's okay if you wanted to solve for L. There's nothing wrong with that. You would just have to deal with some fractions, right? Because you have W divided by 2. But we don't. We have left our fractions alone. So we have an area of L times 400 minus 2L. So we distribute to get our quadratic, 400L minus 2L squared. Okay, we want to maximize your area. Area is a squared unit. Squared equations are called quadratics. So from your quadratic, we're going to have a b value of 400 and an a value of negative 2. Okay, a value of negative 2. So let's see, length equals the negative of 400, that's your b value, divided by 2 times negative 2. Okay, so I get 400 over negative 4. 400 divided by 4 is 100. So I have a length of 100 feet. Okay, 100 feet. 400 divided by 4, or negative 400 divided by negative 4 is 100. Okay, so I have a 100 dimension here and a 100 dimension there. And if my total dimension is 400, then what will my width be? 200. So 400 minus 200 gives me a width of 200. So if all of a sudden now I no longer have 4 sides to my rectangle, my greatest area is no longer a square. So if I have a rectangle sitting out in the middle of nowhere, yes, the square is the best. But once we start taking away your 4 sides and it has less sides, maybe it has more than 4 sides. Maybe it has 6 sides, and you're saying, okay, Manchester, how could it have 6 sides? Well, what if we have a rectangle that we are now cross-fencing? Okay, maybe we have 3 different types of animals, and we want to have horses over here, and goats over there, and cows over there. Well, how many sides do we have? We have 2 widths, right, the top and the bottom, but how many vertical pieces would we have? 4 of them. 1, 2, 3, 4. So in this case, your perimeter would be 4 lengths plus 2 widths. So depending on how many fences you are actually constructing, your perimeter is going to change based upon how many you actually need, right? And that's going to be told to you in your problem. All right, let's flip it over and look at the back, because it's all basically done the same way. So here's example 3. A rectangle is being created on a coordinate axis with the base along the x-axis. Okay, let's draw that. Here's your base along the x-axis and the height along the y-axis in the first quadrant. Okay, check, we got it. The top right corner of the rectangle is sliding along this line. Okay, so this would be our rectangle. It's saying this point right here is moving right along the line. So in other words, this x point is going back and forth. Okay, so it's not a static rectangle. This is a dynamic rectangle that is changing. And if I had my dynamic software, I could show you. It actually looks pretty neat. And we want to figure out what are the dimensions, x and y, that would maximize the rectangular area. Okay? So no longer do we have L and width, right? We have an x and y because we're on a coordinate. The horizontal is your x and the vertical is your y. Okay? Oh, look what it tells us. It tells us the equation of that line. That's very good information. Because we start with our formulas. What's the formula for area? Length times width. So in this case, that's x times y. Right? X is your horizontal, aka length. Y is your vertical, aka width. So your area is x times y. So what else do we know about your equation? Do we have a perimeter of that thing? No, we don't. But do we know how y relates to x? Yes, we do. So we're going to replace y because we're told exactly what y equals. Right? So we're writing this equation in terms of x, negative 1/2 x plus 16. So I replace y with negative 1/2 x plus 16 because that's what y equals. We are told that in the problem. Right? I don't have to calculate how one variable relates to the other one. I am given their relationship right there. So when I distribute, I get this as my quadratic, negative 1/2 x squared plus 16x. Okay, now this is in standard form, so I'm going to have an a value of negative 1/2, and I'm going to have a b value of 16. Okay, just because the squared term comes first. The squared term is always your a value for your formula. Okay, so let's get to doing that. X equals negative b, so the negative of 16 divided by 2 times a, negative 1/2. Okay, so 2 times 1/2, well, that's just 1. So negative 16 divided by negative 1 is 16. So there's my x coordinate, right? This has to be 16 units on the bottom as one of my dimensions. Now the y value, right, I have an equation for y. Y equals negative 1/2 of the x, which was 16, plus 16. Okay, so I'm given an equation in order to calculate my y value. In this case, it turns out to be 8. So the dimensions of my rectangle are 16 by 8. And 16 times 8, well, I don't have a calculator handy, but that's 128 square units. Is that going to be the area of that rectangle with a side of 16 and a height of 8? Okay, so remember the gist is we're wanting to make a quadratic so that we can figure out what the x-coordinate of your vertex is, because that is the coordinate or the dimension that will maximize your area. So we make a quadratic so we can find the vertex, and that will help us to get the dimensions of our rectangle or whatever the shape may be to maximize your area.